Right now, as you're watching this video, there's a massive world spinning through space that's so incredibly huge, it makes Earth look like a tiny pebble next to a watermelon. Jupiter isn't just another planet in our solar system. It's a cosmic monster that could swallow over 1,300 Earths and still have room for dessert. But here's what's really wild about Jupiter's size. When you actually see the numbers, they're going to completely change how you think about our place in the universe. Welcome back to the Lazy Cosmos, where we explore the most mind-bending facts about space. So hit that subscribe button, because today's comparison between Jupiter and Earth is going to leave you questioning everything you thought you knew about planetary scale. Let's begin our cosmic journey by getting comfortable with our home planet Earth, the world we know better than any other place in the universe. When we talk about the size of planets, Earth serves as our perfect starting point because it's the only planet whose scale we can truly understand through our daily experiences. Every step you take, every drive to work, every flight across continents happens on this remarkable blue marble that we call home. Earth has a diameter of exactly 12,742 kilometers, which equals about 7,918 miles if you prefer imperial measurements. Now that might sound like just another number, but let's break this down in ways that will help you truly grasp what this means for our planetary scale comparison. Imagine you decided to take the ultimate road trip around Earth's equator, driving non-stop at a steady highway speed of about 100 kilometers per hour. You would need to drive continuously for approximately 400 hours to complete this incredible journey around our planet. That's nearly 17 full days of driving without stopping to sleep, eat, or even take a bathroom break. If you drove for 8 hours each day, like a normal road trip, it would take you about 50 days to circle our entire planet. This gives us a real sense of Earth's circumference, which measures about 40,075 kilometers around the equator. When we think about walking this distance, even at a brisk pace of 5 kilometers per hour for 10 hours each day, it would take you over 800 days of continuous walking to circle Earth once. Our planet's surface area covers approximately 510 million square kilometers, and about 71% of this surface is covered by oceans and seas. The remaining 29% consists of the continents and islands where all land-dwelling life exists, including every human city, forest, desert, and mountain range. When we look at this surface area, it includes every place you've ever been, every country you might want to visit, and every location that has played a role in human history. From the vast Sahara Desert, spanning 9 million square kilometers, to the tiny country of Monaco, covering just 2 square kilometers, all of these places exist on Earth's surface. The Pacific Ocean alone covers about 165 million square kilometers, which means this single ocean is larger than all of Earth's land areas combined. Earth's mass weighs in at approximately 5.97 trillion kilograms, written scientifically as 5.97 times 10 to the power of 24 kilograms. This number is so enormous that it becomes almost meaningless to our human minds, but we can understand it better through comparisons. If you could somehow collect every car on Earth, all 1.4 billion of them, their combined weight would equal only about 0.000000004% of Earth's total mass. Even if you gathered every building, every ship, every airplane, and every piece of human-made infrastructure on our planet. It would represent just the tiniest fraction of Earth's overall weight. The vast majority of our planet's mass comes from the rock, metal, and molten materials that make up Earth's interior layers. Speaking of Earth's interior, our planet has a fascinating layered structure that contributes to its overall size and mass. At the very center lies Earth's inner core, a solid ball of iron and nickel that measures about 2,440 kilometers in diameter. This inner core is surrounded by the outer core, a liquid layer of molten iron and nickel that extends another 2,300 kilometers outward. Above this sits the mantle, a thick layer of hot rock that makes up about 84% of Earth's total volume and extends roughly 2,900 kilometers from the outer core to the surface. Finally, we have Earth's crust, the thin outer shell, where all life exists, measuring between 5 to 70 kilometers thick, depending on whether you're under the ocean or on a continent. The gravitational pull that holds everything on Earth's surface has a strength that we consider normal because we've lived with it our entire lives. This gravity gives weight to everything around us and keeps our atmosphere from floating away into space. Earth's gravitational acceleration measures 9.8 meters per second squared, which means that when you drop something, it falls toward Earth's center at an increasing speed. This gravitational pull is strong enough to hold our moon in orbit at a distance of about 384,400 kilometers away. And it's this same force that keeps artificial satellites orbiting around our planet. When we consider Earth's place in our solar system, it orbits the Sun at an average distance of about 150 million kilometers, a distance so important in astronomy that scientists use it as a standard measurement called an astronomical unit, or AU. Earth completes one full orbit around the Sun every 365.25 days, which gives us our year, and it rotates on its axis once every 24 hours, creating our day and night cycle. Our planet travels through space around the Sun at an incredible speed of about 107,000 kilometers per hour, though we don't feel this motion because everything on Earth moves together through space. Earth's atmosphere extends about 10,000 kilometers above the surface, though most of the air we breathe exists in the lowest 10 kilometers. This atmospheric layer contains all the weather patterns, clouds, and air that support life on our planet. The atmosphere has a total mass of about 5.15 trillion kilograms, which sounds enormous, but actually represents only about 0.0001% of Earth's total mass. Despite being relatively light compared to the solid planet beneath it, this atmospheric envelope is crucial for maintaining the temperatures and conditions that make Earth habitable. Our planet's magnetic field extends far beyond the atmosphere, creating a protective bubble called the magnetosphere that shields us from harmful solar radiation. This magnetic field is generated by the movement of molten iron in Earth's outer core, and it extends about 65,000 kilometers toward the Sun, and much farther on the side facing away from the Sun. Without this magnetic protection, Earth's atmosphere would gradually be stripped away by solar wind, making our planet uninhabitable. When we look at Earth from space, astronauts often describe the profound experience of seeing our entire world as a single, beautiful sphere floating in the vast darkness of space. From the International Space Station, which orbits about 400 kilometers above Earth's surface, astronauts can see the curvature of our planet, and observe how thin and fragile our atmosphere appears. They can witness entire continents, weather systems, and the division between day and night as Earth rotates beneath them. This perspective, known as the overview effect, helps us understand that despite Earth feeling infinitely large from our ground-based perspective, it's actually a relatively small world in the context of space. Earth's seasonal changes occur because our planet's axis is tilted at an angle of 23.5 degrees relative to its orbital path around the Sun. This tilt means that different parts of Earth receive varying amounts of sunlight throughout the year, creating the seasons we experience. The northern and southern hemispheres take turns being tilted toward or away from the Sun, causing summer and winter to occur at opposite times in each hemisphere. This axial tilt, combined with Earth's spherical shape, also explains why different locations on our planet experience different climates and day lengths. The variety of landscapes and environments on Earth showcases the diversity that can exist on a planet of our size. We have towering mountain ranges, like the Himalayas, with peaks reaching over 8,800 meters above sea level, and deep ocean trenches like the Mariana Trench, which plunges more than 11,000 meters below sea level. Earth's surface features vast plains, dense forests, frozen polar regions, scorching deserts, and everything in between. Each of these environments exists within the relatively thin layer between Earth's solid surface and the edge of our atmosphere. The water on Earth plays a crucial role in making our planet unique and habitable. About 1.386 billion cubic kilometers of water exist on Earth, with roughly 97.5% of this being salt water in oceans and seas. The remaining 2.5% consists of fresh water, most of which is frozen in ice caps and glaciers. Only a tiny fraction of Earth's water is readily available as liquid fresh water in rivers, lakes, and underground sources. This water continuously cycles through evaporation, condensation, and precipitation, distributing heat around our planet and supporting all known life forms. Understanding Earth's size, composition, and characteristics gives us the foundation we need to truly appreciate how remarkable Jupiter's scale really is. Every measurement we've discussed about our home planet, from its 12,742 kilometer diameter to its 510 million square kilometers of surface area, will serve as reference points as we explore the incredible dimensions of our solar system's largest planet. Earth represents everything familiar to us, every place we've known, and every environment that has shaped life as we understand it. Now that we have this solid understanding of our planetary home, we're ready to venture into the mind-bending realm of Jupiter's colossal proportions and discover just how small Earth really is in comparison to this gas giant neighbor. Now that we've established our understanding of Earth as our cosmic reference point, it's time to venture into the realm of truly massive planetary proportions and meet Jupiter, the undisputed heavyweight champion of our solar system. When we begin exploring Jupiter's basic measurements, we immediately encounter numbers that seem almost impossible to comprehend. Yet each one tells us something fascinating about this incredible world that dominates our planetary neighborhood. Jupiter's diameter measures an astounding 142,984 kilometers across its equator. And while that might initially sound like just another large number, the implications of this measurement are absolutely mind-blowing when we compare it to our familiar Earth. To put Jupiter's diameter into perspective Using our Earth reference, imagine taking our entire planet and stretching it out 11.2 times wider. This means that if you could line up Earth side by side across Jupiter's width, you would need more than 11 complete Earth diameters to span from one side of Jupiter to the other. Think about this for a moment. Our planet, which takes nearly 17 days to drive around at highway speeds, would fit across Jupiter's middle more than 11 times. If Earth were shrunk down to the size of a marble, Jupiter would appear roughly the size of a large basketball sitting next to it. This comparison helps us visualize the dramatic difference in scale, but the true magnitude becomes even more apparent when we consider what this size difference means in three-dimensional space. The circumference around Jupiter's equator measures approximately 449,197 kilometers, which is more than 11 times larger than Earth's equatorial circumference of 40,075 kilometers. If you attempted that same hypothetical road trip we discussed around Earth, but this time around Jupiter's equator, you would need to drive continuously for about 4,492 hours at 100 kilometers per hour. That translates to roughly 187 days of non-stop driving. Or if you drove 8 hours per day, like a normal road trip, it would take you about 562 days to complete one circuit around Jupiter. Even at the speed of a commercial airliner flying at 900 kilometers per hour, it would take you nearly 3 weeks of continuous flight to circle Jupiter once. When we examine Jupiter's mass, we encounter numbers that truly showcase this planet's dominance in our solar system. Jupiter weighs approximately 1.898 trillion kilograms, which is about 318 times more massive than Earth. This means that if you could somehow gather 318 identical copies of our entire planet, including every mountain, ocean, continent, and everything else that makes up Earth, their combined mass would equal Jupiter's weight. To help visualize this incredible mass difference, consider that Jupiter contains about 71% of all the planetary mass in our solar system. In other words, if you combine the mass of Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune, and all the moons, asteroids, and other objects orbiting the Sun, Jupiter would still outweigh everything else by more than 2 to 1. The gravitational force generated by Jupiter's enormous mass creates some fascinating effects throughout our solar system. Jupiter's surface gravity measures about 24.79 meters per second squared, which is approximately 2.53 times stronger than Earth's gravity. This means that if you could somehow stand on Jupiter's surface, assuming it had a solid surface to stand on, you would feel more than twice as heavy as you do on Earth. A person who weighs 70 kilograms on Earth would feel like they weigh about 177 kilograms on Jupiter. This intense gravitational pull is strong enough to capture and hold 95 confirmed moons in orbit around Jupiter, creating a miniature solar system with Jupiter at its center. Jupiter's volume represents perhaps the most staggering comparison of all when we measure it against Earth. The total volume of space contained within Jupiter equals approximately 1.43 trillion cubic kilometers, while Earth's volume measures about 1.08 trillion cubic kilometers. This means Jupiter's volume is roughly 1,321 times larger than Earth's volume. To truly understand what this means, imagine trying to fill Jupiter with Earth-sized spheres. You could fit 1,321 complete Earth-sized planets inside Jupiter's volume. and there would still be some empty space left over due to the spherical packing arrangement. Each one of these Earth-sized spheres would contain all the oceans, continents, mountains, cities, and every living thing we've ever known. The surface area of Jupiter, if we consider the visible cloud tops as its surface, covers approximately 61.42 billion square kilometers. Compared to Earth's surface area of 510 million square kilometers, Jupiter has about 120 times more surface area than our planet. This means you could spread out Earth's entire surface, including all the continents and oceans, across Jupiter's surface 120 different times and still cover the entire gas giant. Every country, every ocean, every desert, and every forest on Earth would fit into Jupiter's surface area more than 100 times over. The Great Red Spot alone, Jupiter's famous storm system, covers an area larger than 2 or 3 Earth-sized planets combined. Jupiter's incredible size becomes even more impressive when we consider how far this planet orbits from the Sun. Jupiter maintains an average distance of about 778 million kilometers from the Sun, which equals approximately 5.2 astronomical units. At this distance, Jupiter receives only about 4% of the sunlight that Earth receives, yet it still manages to be the largest planet in our solar system. The reduced solar energy at Jupiter's location means that temperatures in its upper atmosphere average around minus 145 degrees Celsius, creating conditions completely different from the warm, life-supporting environment we enjoy on Earth. Despite orbiting much farther from the Sun than Earth, Jupiter completes one rotation on its axis in just 9 hours and 56 minutes, making it the fastest spinning planet in our solar system. This rapid rotation causes Jupiter to bulge significantly at its equator, making the planet noticeably flattened rather than perfectly spherical. The equatorial diameter measures about 9,275 kilometers larger than the polar diameter, creating an oblate shape that demonstrates the powerful effects of centrifugal force on such a massive, rapidly rotating world. This fast rotation also contributes to Jupiter's complex and dynamic atmospheric patterns, creating the colorful bands and swirling storms that make Jupiter so visually striking. The orbital period of Jupiter tells us another fascinating aspect of this giant planet's behavior in our solar system. Jupiter takes approximately 11.86 Earth years to complete one full orbit around the Sun, moving through space at an average orbital velocity of about 47,000 kilometers per hour. While this might seem slow compared to Earth's orbital speed of 107,000 kilometers per hour, Jupiter's much larger orbital path means it covers an enormous distance during each orbit. In fact, Jupiter travels about 4.9 billion kilometers during each complete trip around the Sun, compared to Earth's orbital distance of about 940 million kilometers per year. Jupiter's magnetic field represents another area where this planet's size and power become apparent. The magnetic field generated by Jupiter is approximately 20,000 times stronger than Earth's magnetic field, creating a magnetosphere so large that it extends well beyond the orbits of Jupiter's 4 largest moons. If we could somehow see Jupiter's magnetosphere from Earth, it would appear larger in our sky than the full moon, even though Jupiter itself appears as just a bright point of light. This powerful magnetic field traps charged particles from the solar wind, creating intense radiation belts around Jupiter that would be deadly to human explorers without proper shielding. The atmospheric pressure on Jupiter increases dramatically as you descend through its layers of gas. At the level we consider Jupiter's surface, the atmospheric pressure equals about 100 times Earth's sea level pressure. As you continue descending into Jupiter's interior, the pressure continues to increase until it reaches levels millions of times greater than anything we experience on Earth. Under these extreme pressures, hydrogen gas becomes compressed into a metallic state that doesn't exist naturally anywhere on Earth, demonstrating the incredible physical conditions created by Jupiter's massive size and gravitational compression. Jupiter's density provides another interesting comparison point with Earth. Despite being so much more massive than Earth, Jupiter actually has a much lower density because it consists primarily of lightweight gases rather than solid rock and metal. Jupiter's average density measures about 1.326 grams per cubic centimeter, while Earth's density averages 5.514 grams per cubic centimeter. This means that Earth is actually more than 4 times denser than Jupiter, illustrating the fundamental difference between rocky planets like Earth and gas giants like Jupiter. When we consider Jupiter's escape velocity, we find another measurement that demonstrates this planet's incredible gravitational strength. The escape velocity from Jupiter measures about 59.5 kilometers per second, compared to Earth's escape velocity of 11.2 kilometers per second. This means that any spacecraft leaving Jupiter's surface would need to reach speeds more than 5 times faster than spacecraft leaving Earth. This enormous escape velocity explains why Jupiter has been able to hold on to its massive atmosphere of hydrogen and helium for billions of years, while smaller planets have lost much of their original atmospheres to space. These raw numbers paint a picture of a world so massive and powerful that it fundamentally shapes the structure and behavior of our entire solar system. Jupiter's gravitational influence affects the orbits of asteroids, comets, and even other planets, acting as both a cosmic vacuum cleaner that captures dangerous objects and a gravitational shepherd that helps maintain orbital stability throughout our solar system. As we absorb these incredible measurements and comparisons, we begin to understand that Jupiter isn't just another planet in our solar system. It's a dominant force that has played a crucial role in making Earth's stable, life-supporting orbit possible. These numbers represent the foundation for understanding how truly insignificant Earth's size becomes when compared to this gas giant neighbor, and they prepare us for even more mind-bending revelations about Jupiter's scale and influence in the cosmos. Now that we've explored the basic measurements that define Jupiter's enormous scale, it's time to dive deeper into what these numbers actually mean in terms of the three-dimensional space that Jupiter occupies in our solar system. When we talk about volume, we're discussing the total amount of space contained within an object, and this is where Jupiter's true dominance becomes absolutely mind-boggling. The concept of volume can be challenging to visualize because we're dealing with three-dimensional space rather than simple linear measurements, but understanding Jupiter's volume compared to Earth's will fundamentally change how you perceive the scale of our cosmic neighborhood. Jupiter's total volume measures approximately 1.431 trillion cubic kilometers, a number so vast that our minds struggle to comprehend its true meaning. To put this in perspective, imagine a cube where each side measures 112,000 kilometers in length. This cube would contain roughly the same volume as Jupiter, and it would be so large that Earth could fit along each edge of this cube about 9 times. But Jupiter isn't cube-shaped, of course. It's roughly spherical. which means all of this incredible volume is contained within a giant ball of gas and liquid that spins through space at the outer edge of our solar system's inner region. When we compare Jupiter's volume to Earth's volume of 1.083 trillion cubic kilometers, we discover that Jupiter contains about 1,321 times more space than our entire planet. This famous comparison means that you could theoretically fit 1,321 Earth-sized spheres inside Jupiter's volume, assuming perfect packing efficiency. However, the reality of how spheres pack together in three-dimensional space means that you couldn't actually fit quite that many complete Earth-sized objects inside Jupiter due to the empty spaces that naturally occur between spheres. Even accounting for this packing inefficiency, you could still fit well over 1,000 complete Earths inside Jupiter with room to spare. To help visualize this incredible volume difference, let's think about it in terms of familiar objects and scaling. If Earth were reduced to the size of a ping pong ball, measuring about 4 centimeters in diameter, Jupiter would be a sphere measuring about 44.8 centimeters in diameter, roughly the size of a large exercise ball or beach ball. Now imagine trying to fit 1,321 ping pong balls inside that exercise ball. Even though it seems impossible, the mathematics of three-dimensional volume scaling makes this comparison accurate. The difference between two-dimensional area and three-dimensional volume creates these dramatic scaling effects that can seem counterintuitive to our everyday experience. Consider what it would mean if we could somehow hollow out Jupiter and use it as a container for storing Earth-sized planets. Each Earth that we placed inside would contain every ocean, every continent, every mountain range, every city, and every single thing that makes up our world. The first Earth would contain all of human history, every person who has ever lived, and every location that has played a role in the development of our civilization. The second Earth would duplicate all of this completely. By the time we had filled Jupiter with hundreds of Earths, we would have created a storage container holding hundreds of complete worlds, each with their own versions of the Amazon rainforest, the Sahara Desert, the Himalayan mountains, and every other geographical feature we know. The mathematical relationship between diameter and volume helps explain why Jupiter's volume is so dramatically larger than Earth's, even though Jupiter's diameter is only about 11 times larger. Volume increases as the cube of the diameter, which means that when you double the diameter of a sphere, you increase its volume by 8 times. When you increase the diameter by 11.2 times, as we see with Jupiter compared to Earth, the volume increases by 11.2 times, 11.2 times, 11.2, which equals approximately 1,404 times. This mathematical relationship explains why small increases in planetary diameter create enormous increases in planetary volume. Jupiter's massive volume also means that this planet contains an incredible amount of empty space relative to solid matter. If Earth were somehow expanded to Jupiter's size while maintaining the same density, the resulting planet would be impossibly massive and would likely collapse under its own gravity to form a much smaller, denser object. Instead, Jupiter maintains its enormous size because it consists primarily of lightweight hydrogen and helium gases that can expand to fill vast amounts of space without adding proportional mass. This composition allows Jupiter to occupy an enormous volume while maintaining a density low enough to remain stable as a planet, rather than collapsing into a much denser object. The concept of surface area becomes fascinating when we consider Jupiter's three-dimensional volume. Jupiter's surface area, measured at the level of its visible cloud tops, covers approximately 61.42 billion square kilometers. This surface area is about 120 times larger than Earth's surface area of 510 million square kilometers. To visualize this difference, imagine being able to unwrap Jupiter's surface like peeling an orange and laying it flat. The resulting surface would be large enough to contain 120 complete copies of Earth's entire surface, including all continents, oceans, and everything else that covers our planet. This enormous surface area means that Jupiter experiences weather patterns and atmospheric phenomena on a scale that dwarfs anything we see on Earth. The Great Red Spot, Jupiter's most famous atmospheric feature, is a storm system that has been raging for hundreds of years and covers an area larger than 2 or 3 Earth-sized planets. The bands of clouds that circle Jupiter's atmosphere extend across distances that would span multiple Earth diameters, creating weather systems so large that our entire planet would be lost within a single Jovian storm cell. When we think about the internal structure that fills Jupiter's massive volume, we discover layers and regions that extend across distances larger than entire planets. Jupiter's core, if it exists as a distinct solid or liquid region, might have a diameter comparable to Earth's entire diameter. The metallic hydrogen layer that surrounds this core extends across thousands of kilometers in all directions, creating a region of exotic matter that occupies more space than multiple Earth-sized volumes. The outer atmosphere, where we see Jupiter's colorful cloud bands, extends across distances that would encompass the orbits of multiple moons if we were to scale this system down to Earth-size proportions. Jupiter's gravitational influence extends its effective presence far beyond its physical volume through its gravitational field. The Hill sphere, which represents the region where Jupiter's gravity dominates over the Sun's gravitational pull, extends approximately 53 million kilometers from Jupiter's center. This gravitational sphere of influence has a volume roughly 740 million times larger than Jupiter's physical volume, demonstrating how a massive planet's presence extends far beyond its visible boundaries. Within this enormous gravitational domain, Jupiter controls the motion of its 95 known moons and countless smaller objects, creating a gravitational ecosystem that spans millions of cubic kilometers of space. The rate at which Jupiter spins on its axis creates additional fascinating volume-related effects throughout its massive structure. Jupiter completes one full rotation in just 9 hours and 56 minutes, which means that different parts of Jupiter's enormous volume are moving at vastly different speeds. Points on Jupiter's equator travel at about 45,300 kilometers per hour as the planet rotates, while regions closer to Jupiter's poles move much more slowly. This differential rotation creates complex dynamics throughout Jupiter's massive volume, generating the energy that drives Jupiter's atmospheric circulation patterns and contributes to the formation of its distinctive cloud bands. The thermal properties of Jupiter's enormous volume also create interesting phenomena that don't exist on smaller planets like Earth. Jupiter actually radiates more heat into space than it receives from the Sun, generating this excess energy through the slow gravitational compression of its massive volume. The process of gravitational contraction releases energy throughout Jupiter's interior, warming the planet from within and creating temperature gradients that drive atmospheric circulation across its vast surface area. This internal heat source means that Jupiter's atmospheric dynamics are powered by energy generated within its own massive volume, rather than relying solely on solar heating like Earth's weather systems. When we consider how long it would take to explore Jupiter's enormous volume, the scale becomes even more impressive. If we could somehow travel through Jupiter's interior at the speed of a commercial airliner, about 900 kilometers per hour, it would take us about 159 hours, or nearly 7 full days, to travel from one side of Jupiter to the other through its center. This journey would take us through regions of gas, liquid, and possibly solid materials under pressures and temperatures that don't exist anywhere on Earth. Traveling through a volume large enough to contain more than 1,000 complete worlds like our own. The gravitational effects of Jupiter's massive volume influence objects throughout our solar system, demonstrating how three-dimensional space and gravitational fields interact across cosmic distances. Jupiter's gravity affects the orbits of asteroids in the asteroid belt, creates gaps in the ring of space debris between Mars and Jupiter, and influences the paths of comets that venture into the inner solar system. Some asteroids, called Trojan asteroids, share Jupiter's orbit around the Sun, trapped in gravitational stable points created by the interaction between Jupiter's massive volume and the Sun's gravitational field. Understanding Jupiter's volume in comparison to Earth helps us appreciate not just the scale of this massive planet, but also the incredible efficiency of gravitational forces in organizing matter across such vast distances. Every cubic kilometer of Jupiter's enormous volume contributes to the planet's overall gravitational field, which in turn shapes the structure of our entire solar system. This massive volume of gas and liquid creates a gravitational anchor that has influenced the formation and evolution of planetary orbits for billions of years, demonstrating how size and volume translate directly into cosmic influence and power. As we contemplate these volume comparisons between Jupiter and Earth, we begin to understand that we live on what is essentially a tiny island of solid matter in a solar system dominated by vast volumes of gas, liquid, and empty space. Our familiar Earth, with all its continents, oceans, and everything we've ever known, represents just a tiny fraction of the three-dimensional space occupied by our giant planetary neighbor. And this realization prepares us for even more remarkable discoveries about how Jupiter's massive volume translates into gravitational dominance and cosmic influence throughout our solar system. As we continue our journey through Jupiter's incredible proportions, we now turn our attention to perhaps the most important characteristic that defines this giant planet's role in our solar system: its absolutely staggering mass and the gravitational dominance that flows from it. While volume tells us about the space Jupiter occupies, mass tells us about the actual amount of matter packed into that enormous sphere. And this is where Jupiter truly reveals its cosmic significance. Mass creates gravity. Gravity shapes orbits, and orbits determine the structure of entire planetary systems, making Jupiter's mass the fundamental force that has helped shape our solar system into the stable, organized collection of worlds we see today. Jupiter's total mass weighs in at an almost incomprehensible 1.898, followed by 27 zeros kilograms, or in scientific notation, 1.898 times 10 to the 27th power kilograms. To put this enormous number into perspective, using our familiar Earth reference, Jupiter contains about 317.8 times more matter than our entire planet. This means that if you could somehow gather 318 complete copies of Earth, including every mountain, every ocean, every continent, every building, every person, and every grain of sand, their combined mass would roughly equal Jupiter's total mass. Each of those 318 Earths would represent everything we've ever known about solid, rocky planets. Yet Jupiter contains all of that matter and more in the form of compressed gases and liquids. The distribution of mass throughout our solar system reveals just how dominant Jupiter really is among the planets. When astronomers calculate the total mass of all planets orbiting our Sun, they discover that Jupiter alone contains about 71% of all planetary mass in our solar system. Saturn, the second largest planet, contains about 21% of the total planetary mass, which means that Jupiter and Saturn together account for more than 90% of all the matter organized into planets around our Sun. All the remaining planets, including Earth, Mars, Venus, Mercury, Uranus, and Neptune, combined contain less than 10% of the total planetary mass, with Earth representing only about 0.03% of all planetary matter. This incredible mass concentration gives Jupiter a gravitational influence that extends far beyond its physical boundaries and affects virtually every object in our solar system. Gravity is directly proportional to mass, which means that Jupiter's 318 times greater mass creates a gravitational field that is correspondingly powerful. At Jupiter's cloud tops, the gravitational acceleration measures about 24.79 meters per second squared, compared to Earth's surface gravity of 9.8 meters per second squared. This means that if you could somehow stand on Jupiter's surface, you would experience about 2.53 times your normal Earth weight, making every movement significantly more challenging and demonstrating the practical effects of Jupiter's massive gravitational field. Jupiter's gravitational dominance extends throughout a region of space called its Hill sphere, which represents the area where Jupiter's gravity overpowers the Sun's gravitational influence on small objects. This Hill sphere extends approximately 53 million kilometers from Jupiter's center, creating a gravitational domain roughly 740 times larger than Jupiter's physical radius. Within this enormous sphere of influence, Jupiter controls the motion of 95 confirmed moons, ranging from tiny irregular chunks of rock just a few kilometers across to massive worlds like Ganymede, which is actually larger than the planet Mercury. These moons orbit Jupiter in complex patterns, with some moving in perfectly circular orbits close to Jupiter's equator, while others follow highly elliptical paths that take them millions of kilometers away from their parent planet. The four largest moons of Jupiter, known as the Galilean moons, because Galileo Galilei discovered them in 1610, demonstrate the incredible power of Jupiter's gravitational field. Io, Europa, Ganymede, and Callisto orbit Jupiter at distances ranging from about 422,000 kilometers to 1.88 million kilometers. Yet Jupiter's gravity keeps them locked in stable orbits, despite the competing gravitational influence of the Sun. These moons are substantial worlds in their own right, with Ganymede measuring larger than Mercury and Europa possibly harboring more liquid water than all of Earth's oceans combined. Yet they remain gravitationally bound to Jupiter throughout their billions of years of orbital motion. Jupiter's massive gravitational field also plays a crucial role in protecting the inner solar system from potentially dangerous objects. Many comets that venture into the inner solar system from the distant Kuiper Belt and Oort cloud encounter Jupiter's gravitational influence during their journeys toward the Sun. Some of these comets get captured into orbits around Jupiter, while others receive gravitational kicks that either accelerate them out of the solar system entirely or send them crashing into Jupiter itself. The famous impact of Comet Shoemaker-Levy 9 in 1994 demonstrated this protective effect dramatically, as Jupiter's gravity first tore the comet apart through tidal forces, then drew the fragments into collision courses that resulted in spectacular impacts visible from Earth. The gravitational relationship between Jupiter and the Sun creates fascinating dynamics that affect the entire solar system. While the Sun contains about 1,048 times more mass than Jupiter, Jupiter's substantial mass is still significant enough to cause the Sun itself to wobble slightly as both objects orbit around their common center of mass, called the barycenter. This barycenter lies about 742,000 kilometers from the Sun's center, just outside the Sun's surface, which means that the Sun actually orbits around a point in space rather than remaining perfectly stationary at the center of our solar system. This gravitational dance between the Sun and Jupiter creates subtle variations in the Sun's position that astronomers can detect and use to discover similar planetary systems around other stars. Jupiter's gravitational influence extends to the asteroid belt, the region of space between Mars and Jupiter that contains thousands of rocky objects left over from the formation of our solar system. Jupiter's gravity has prevented these asteroids from coalescing into a planet, instead keeping them scattered in a broad belt of debris. Additionally, Jupiter's gravitational field creates gaps in the asteroid belt called Kirkwood gaps, where objects cannot maintain stable orbits due to orbital resonances with Jupiter. These resonances occur when asteroids orbit the Sun in periods that are simple fractions of Jupiter's orbital period, causing repeated gravitational tugs that eventually destabilize their orbits and clear out these regions of space. The concept of orbital resonance demonstrates another aspect of Jupiter's gravitational dominance throughout our solar system. Several objects in our solar system maintain orbital periods that are simple mathematical ratios of Jupiter's 11.86-year orbital period. The Trojan asteroids, for example, share Jupiter's orbit around the Sun, but remain clustered in two groups located 60 degrees ahead of and behind Jupiter in its orbit. These stable gravitational points, called Lagrange points, exist because of the complex gravitational interaction between the Sun, Jupiter, and these smaller objects, creating regions where the combined gravitational forces balance perfectly to maintain stable orbits. Jupiter's rapid rotation period of 9 hours and 56 minutes, combined with its enormous mass, creates additional gravitational effects that don't exist on smaller, more slowly rotating planets. The centrifugal force, generated by Jupiter's rapid rotation, causes the planet to bulge significantly at its equator, creating an oblate shape where the equatorial diameter exceeds the polar diameter by about 9,275 kilometers. This equatorial bulge redistributes Jupiter's mass in a way that affects its gravitational field, creating a slightly stronger gravitational pull at the poles compared to the equator, and influencing the orbital dynamics of Jupiter's closest moons. The escape velocity from Jupiter provides another way to understand the incredible strength of its gravitational field. Any object leaving Jupiter's surface would need to reach a velocity of about 59.5 kilometers per second to escape completely from Jupiter's gravitational influence. This escape velocity is more than 5 times greater than Earth's escape velocity of 11.2 kilometers per second, illustrating why Jupiter has been able to retain its massive atmosphere of hydrogen and helium for billions of years, while smaller planets have lost significant portions of their original atmospheres to space. The enormous energy required to escape Jupiter's gravity also explains why spacecraft missions to Jupiter require such powerful rockets and careful trajectory planning to achieve their goals. Jupiter's internal structure reflects the incredible pressures created by its massive gravitational field, compressing the planet's material toward its center. As you descend through Jupiter's atmosphere, the pressure increases dramatically, eventually reaching levels millions of times greater than Earth's atmospheric pressure. Under these extreme conditions, hydrogen gas becomes compressed into a metallic state that doesn't exist naturally on Earth, creating a layer of metallic hydrogen that might extend through much of Jupiter's interior. The gravitational compression also generates heat through the conversion of gravitational potential energy into thermal energy, causing Jupiter to radiate about 1.67 times more energy into space than it receives from the Sun. The tidal forces generated by Jupiter's massive gravitational field create fascinating effects on its moons and other nearby objects. The moon Io experiences such strong tidal forces from Jupiter that its solid surface rises and falls by up to 100 meters during each orbit, generating enormous amounts of friction and heat within Io's interior. This tidal heating makes Io the most volcanically active world in our solar system, with hundreds of active volcanoes continuously reshaping its surface. Europa experiences similar but less extreme tidal heating that may keep a subsurface ocean liquid beneath its icy surface, creating one of the most promising locations in our solar system for the search for extraterrestrial life. Jupiter's gravitational field also affects the long-term stability of planetary orbits throughout our solar system. Computer simulations of solar system dynamics show that without Jupiter's massive gravitational presence, the orbits of the terrestrial planets, including Earth, would be much less stable over geological timescales. Jupiter's gravity helps maintain the nearly circular orbits of the inner planets by preventing gravitational perturbations from building up into orbit, destabilizing resonances. This gravitational guardianship has likely played a crucial role in maintaining Earth's stable climate and making the development of complex life possible over billions of years. The detection of gravitational waves, ripples in space-time itself, represents one of the most cutting-edge ways that scientists study massive objects like Jupiter. While Jupiter's mass isn't large enough to generate detectable gravitational waves through its normal orbital motion, the techniques used to detect these incredibly subtle distortions in spacetime help us understand how mass and gravity operate on cosmic scales. Jupiter's massive gravitational field serves as a natural laboratory for testing our understanding of gravity and general relativity, particularly in how massive objects curve spacetime and influence the motion of nearby matter and energy. As we contemplate Jupiter's incredible mass and gravitational dominance, we begin to understand that this giant planet isn't just a large object floating in space, but rather a fundamental organizing force that has shaped the architecture of our entire solar system. Every asteroid orbit, every comet trajectory, and every planetary motion bears the influence of Jupiter's massive gravitational field, making this giant planet an essential component in the cosmic machinery that has created and maintained the stable, life-supporting conditions we enjoy on Earth. The mass concentrated within Jupiter's enormous volume represents power on a truly cosmic scale, demonstrating how matter and gravity work together to create order and structure across the vast distances of interplanetary space. As we delve deeper into understanding Jupiter's incredible scale compared to Earth, we must explore one of the most fundamental differences between these two worlds: what they're actually made of. The composition of a planet determines not only its size and mass, but also its behavior, its appearance, and its role in the solar system. While Earth is a solid, rocky world built from metals and silicate minerals, Jupiter represents an entirely different category of planet, composed primarily of the same lightweight gases that fuel stars. This compositional difference explains how Jupiter can be so much larger than Earth while still maintaining its planetary structure, and it reveals fascinating insights about how different types of worlds form and evolve in our cosmic neighborhood. Jupiter consists primarily of hydrogen, the simplest and most abundant element in the universe. Approximately 89% of Jupiter's atmosphere is hydrogen gas, existing in various forms throughout the planet's massive interior. Near Jupiter's surface, this hydrogen exists as ordinary molecular hydrogen gas, the same substance that we might use to fill balloons or power fuel cells on Earth. However, as we descend deeper into Jupiter's interior, the enormous pressure created by the planet's massive gravitational field compresses this hydrogen into increasingly exotic states. In the deeper regions of Jupiter's interior, pressures reach levels so extreme that hydrogen transforms into a metallic state that doesn't exist anywhere on Earth's surface, creating a form of matter that conducts electricity like copper or aluminum, but consists entirely of hydrogen atoms. The second most abundant component of Jupiter's composition is helium, making up about 10% of the planet's total mass. This helium exists mixed with hydrogen throughout Jupiter's atmosphere and interior, creating a cosmic blend of the two lightest elements in the periodic table. Helium is completely inert under normal conditions, meaning it doesn't react chemically with other elements. But under the extreme conditions inside Jupiter, even this noble gas contributes to the complex physical processes that maintain the planet's structure and generate its internal heat. The combination of hydrogen and helium gives Jupiter its relatively low density compared to rocky planets, allowing it to maintain its enormous volume without collapsing under its own gravitational weight. In stark contrast, Earth's composition tells the story of a world built from much heavier elements forged inside ancient stars and distributed throughout space by stellar explosions. Earth's core consists primarily of iron and nickel, dense metals that sank toward our planet's center during the early stages of its formation, when Earth was still hot and molten. Surrounding this metallic core lies Earth's mantle, composed mainly of silicate minerals containing silicon, oxygen, magnesium, and iron. These minerals form the rocky foundation that supports Earth's thin outer crust, where all surface life exists. The average density of Earth measures 5.514 grams per cubic centimeter, more than 4 times denser than Jupiter's average density of 1.326 grams per cubic centimeter. The remaining 1% of Jupiter's composition includes traces of heavier elements that astronomers call metals, even though many of these aren't metallic in the traditional sense. These trace elements include water vapor, methane, ammonia, hydrogen sulfide, and various other compounds that create Jupiter's colorful atmospheric features. Despite representing only a tiny fraction of Jupiter's total mass, these trace compounds play crucial roles in creating the complex weather patterns, cloud formations, and distinctive coloration that make Jupiter so visually striking. The water vapor condenses into clouds at certain altitudes. Ammonia creates different types of clouds at other levels, and various sulfur compounds contribute to the reddish and brownish colors we observe in Jupiter's atmospheric bands. Earth's atmospheric composition provides a fascinating contrast to Jupiter's gas giant atmosphere. Earth's atmosphere consists of about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, and other gases. This atmosphere represents less than 0.0001% of Earth's total mass, forming a thin envelope around our solid planet rather than making up the bulk of the world itself. Earth's atmosphere extends only about 100 kilometers above the surface before transitioning into the vacuum of space, while Jupiter's atmosphere gradually increases in density and pressure as you descend, eventually transitioning into liquid and possibly solid states without any clear boundary between atmosphere and interior. The temperature differences between Earth and Jupiter reflect their different compositions and distances from the Sun. Earth's surface temperature averages about 15 degrees Celsius, maintained within a narrow range suitable for liquid water by our planet's solid surface, protective atmosphere, and optimal distance from the Sun. Jupiter's outer atmosphere, by contrast, experiences temperatures of approximately minus 145 degrees Celsius, cold enough to freeze most gases solid. However, Jupiter's interior generates significant heat through gravitational compression, creating a temperature gradient that reaches several thousand degrees in the planet's core, possibly hotter than the surface of the Sun. The process of planetary formation explains how these dramatically different compositions came to exist in the same solar system. In the early stages of our solar system's development, a disk of gas, dust, and debris surrounded the young Sun. Closer to the Sun, where Earth formed, high temperatures prevented lightweight gases like hydrogen and helium from condensing into solid particles. Only heavier elements could form solid grains in these inner regions, leading to the formation of rocky planets with metallic cores. Farther from the Sun, where Jupiter formed, temperatures were cold enough for water, methane, and other compounds to freeze into solid particles, providing the building blocks for larger planetary cores. Once Jupiter's core reached a critical mass of approximately 10 to 15 Earth masses, its gravitational field became strong enough to capture and retain large amounts of hydrogen and helium gas directly from the surrounding solar nebula. This process, called runaway accretion, allowed Jupiter to grow rapidly by accumulating the abundant lightweight gases that made up most of the material in the early solar system. The timing of this process was crucial, as Jupiter had to reach its critical mass before the young Sun's stellar winds dispersed the hydrogen and helium gas from the inner solar system. The different compositions of Earth and Jupiter create vastly different internal structures and physical processes. Earth's solid surface allows for geological processes like plate tectonics, volcanic activity, and erosion that continuously reshape the planet's appearance and create diverse environments for life. Earth's magnetic field, generated by the motion of molten iron in the outer core, protects our planet's atmosphere from being stripped away by solar wind. The interaction between Earth's solid surface, liquid oceans, and gaseous atmosphere creates the complex climate system that maintains conditions suitable for life. Jupiter's gaseous composition creates entirely different types of physical processes and phenomena. The absence of a solid surface means that Jupiter's atmospheric dynamics operate on scales and with intensities unknown on rocky planets. The Great Red Spot, Jupiter's most famous atmospheric feature, is a storm system larger than Earth that has been raging for centuries, powered by heat from Jupiter's interior and the complex interactions between different atmospheric layers. The rapid rotation of Jupiter's massive gaseous bulk creates powerful atmospheric circulation patterns that generate the distinctive banded appearance we observe from space. The different compositions also affect how these planets interact with their surroundings. Earth's solid surface and relatively thin atmosphere mean that impacts from asteroids and comets can create lasting scars like impact craters that remain visible for millions of years. Jupiter's thick, gaseous atmosphere, by contrast, completely absorbs incoming objects, as dramatically demonstrated by the impact of Comet Shoemaker-Levy 9 in 1994, which created temporary dark spots in Jupiter's atmosphere that gradually faded over months and years. The magnetic fields generated by Earth and Jupiter reflect their different internal compositions and structures. Earth's magnetic field originates from the movement of liquid iron in our planet's outer core, creating a relatively simple dipolar field similar to a bar magnet. Jupiter's magnetic field, generated by the movement of metallic hydrogen in its interior, is about 20,000 times stronger than Earth's field and has a more complex structure with multiple poles and irregularities. This powerful magnetic field creates intense radiation belts around Jupiter that would be lethal to unprotected human explorers. The evolution of planetary atmospheres also depends heavily on composition and mass. Earth's moderate mass allows it to retain its atmosphere while still permitting the escape of lighter gases over geological timescales. This selective atmospheric loss has contributed to the development of Earth's oxygen-rich atmosphere through billions of years of geological and biological processes. Jupiter's enormous mass prevents virtually any atmospheric escape, allowing it to retain essentially the same atmospheric composition it had when it first formed billions of years ago. The presence of water in different forms on Earth and Jupiter illustrates another aspect of how composition affects planetary characteristics. Earth's water exists primarily as liquid oceans, covering most of the planet's surface, with smaller amounts present as atmospheric vapor and polar ice. Jupiter contains significantly more water than Earth in absolute terms, but this water exists primarily as vapor mixed throughout the planet's massive atmosphere, with some possibly condensed as ice crystals in the cooler upper atmospheric layers. The study of Jupiter's composition has provided crucial insights into the formation and evolution of planetary systems throughout the universe. Many of the exoplanets discovered around other stars are gas giants similar to Jupiter, suggesting that the processes that created Jupiter's unique composition and structure are common throughout our galaxy. Understanding how lightweight gases can accumulate into massive planets helps astronomers interpret observations of distant planetary systems and develop theories about how planetary formation proceeds under different conditions. The compositional differences between Earth and Jupiter also highlight the incredible diversity of worlds that can exist within a single planetary system. From the dense metallic core of Earth to the exotic metallic hydrogen deep within Jupiter. These two planets demonstrate the wide range of physical conditions and states of matter that exist in our cosmic neighborhood. Each composition creates its own unique set of physical processes, atmospheric dynamics, and environmental conditions, showing how the fundamental building blocks of matter can combine in dramatically different ways to create the rich variety of worlds we observe throughout our solar system. As we contemplate these profound compositional differences between Earth and Jupiter, we gain a deeper appreciation for the complex processes that govern planetary formation and evolution. The lightweight gases that make Jupiter so massive also make it fundamentally different from our rocky homeworld, creating a planet where familiar concepts like solid ground, fixed weather patterns, and stable surface features simply don't exist. Instead, Jupiter represents a dynamic, ever-changing world of gas and liquid, where the very elements that make up stars swirl in massive atmospheric systems under pressures and temperatures that transform matter into exotic states found nowhere else in our solar system. To truly understand why Jupiter became such a massive giant compared to Earth, we need to travel back in time about 4.6 billion years to witness the birth of our solar system and follow the remarkable story of how these two very different worlds came to exist. The formation of Jupiter and Earth tells us a fascinating tale of cosmic timing, location, and the delicate balance of forces that shaped our entire planetary neighborhood. This story begins in a vast cloud of gas and dust floating in space, and through a series of extraordinary events, it culminates in the creation of both our small, rocky homeworld and the gas giant that dominates our solar system today. Our solar system began its existence as a massive molecular cloud, sometimes called a stellar nebula, composed primarily of hydrogen and helium gas, mixed with tiny particles of dust and ice. This cloud was incredibly vast, measuring several light years across, and containing enough material to form not just our sun, but potentially hundreds of other stars as well. For millions of years, this cloud drifted peacefully through space, slowly rotating and gradually cooling as it radiated heat into the cosmic void. The density within this cloud was extremely low, far less dense than the best vacuum we can create on Earth. Yet it contained all the raw materials that would eventually become our sun, all the planets, and everything else in our solar system. The transformation from a peaceful cloud to an active stellar nursery began when something disturbed the cloud's equilibrium. This disturbance might have been the shock wave from a nearby supernova explosion, the gravitational influence of a passing star, or perhaps the collision with another molecular cloud. Whatever the cause, this disturbance created regions of slightly higher density within the cloud, and gravity immediately began to pull more material toward these denser areas. As more matter accumulated, the gravitational attraction grew stronger, creating a runaway process that caused the cloud to begin collapsing in on itself. As the cloud collapsed under its own gravity, it began to spin faster, much like an ice skater spinning faster when pulling in their arms. This increasing rotation caused the collapsing cloud to flatten into a disk shape, with most of the material concentrated in a dense, hot region at the center that would eventually become our sun. The remaining material spread out in a rotating disk called a protoplanetary disk or solar nebula, extending billions of kilometers from the central proto-sun. Within this disk, the temperature varied dramatically with distance from the center, creating different zones where different types of materials could exist in solid form. In the inner regions of this protoplanetary disk, where Earth would eventually form, temperatures reached several hundred degrees Celsius due to the heat radiating from the forming sun. These high temperatures meant that only materials with very high melting points could exist as solid particles. Metals like iron and nickel, along with rocky minerals containing silicon, magnesium, and oxygen, could condense into solid grains, but lighter materials like water, methane, and ammonia remained as gases. This created a region dominated by what astronomers call refractory materials, substances that can withstand high temperatures without vaporizing. Much farther from the Sun, in the region where Jupiter would form, temperatures were much colder, typically below minus 150 degrees Celsius. At these frigid temperatures, not only could metals and rocky materials condense into solid particles, but water could also freeze into ice, along with other compounds like methane, ammonia, and carbon dioxide. This region, beyond what scientists call the snow line or frost line, contained much more solid material per unit volume than the inner solar system, providing the building blocks for much larger planetary cores. The process of planetary formation began with the gradual accumulation of these solid particles through a process called accretion. Tiny dust grains stuck together when they collided, forming slightly larger particles. These larger particles had stronger gravitational fields, allowing them to attract and capture even more material. Over millions of years, this process built up larger and larger objects, progressing from dust grains to pebbles, from pebbles to boulders, from boulders to mountains, and eventually to objects large enough to be called planetesimals, measuring kilometers to hundreds of kilometers across. In the inner solar system, where Earth formed, this accretion process continued relatively slowly because the available solid material consisted mainly of dense metals and rocky minerals. The planetesimals that formed in this region grew by colliding and merging with each other, gradually building up the mass that would eventually become the terrestrial planets. Earth's formation involved countless collisions between these rocky planetesimals, with each impact adding more mass and generating enormous amounts of heat that kept the growing planet molten for millions of years. Jupiter's formation story took a dramatically different path due to its location beyond the snow line. In this cold region, the available solid material included not only metals and rocks, but also abundant ice made from water, methane, ammonia, and other frozen compounds. This meant that Jupiter's region contained several times more solid building material per unit volume than Earth's region, allowing planetary cores to grow much more rapidly. Computer models suggest that Jupiter's solid core grew to about 10 to 15 times Earth's mass within just a few million years, much faster than the terrestrial planets were accumulating mass. This rapid core formation was crucial to Jupiter's ultimate size because it triggered a process called runaway gas accretion. Once Jupiter's solid core reached this critical mass threshold, its gravitational field became strong enough to begin capturing and holding on to the hydrogen and helium gas that made up most of the material in the protoplanetary disk. Initially, this gas formed a relatively thin atmosphere around Jupiter's solid core. But as more gas accumulated, the growing planet's gravity became even stronger, allowing it to capture gas at an accelerating rate. The timing of this runaway accretion phase was critical because it had to occur before the young sun became fully active and began generating strong stellar winds. In the early stages of stellar formation, Protostars go through a phase called the T-Tauri phase, during which they generate powerful stellar winds that blow away the remaining gas from the protoplanetary disk. Jupiter had to complete most of its gas accretion before this phase began, or it would have remained a relatively small, rocky planet similar to Earth, but located much farther from the Sun. Jupiter's rapid growth during this period had profound effects on the rest of the forming solar system. As Jupiter accumulated mass and grew larger, its gravitational influence began to affect the orbits of planetesimals and other forming planets throughout the solar system. Some computer models suggest that Jupiter may have migrated inward toward the Sun during its early formation, potentially disrupting the formation of planets in the inner solar system before later migrating back to its current position. This process, known as planetary migration, could explain some of the unusual characteristics of our solar system compared to other planetary systems discovered around distant stars. The formation of Jupiter's extensive moon system occurred during and after the planet's main accretion phase. As Jupiter grew larger and its gravitational field stronger, it began to capture objects from the surrounding region of the solar system. Some of these captured objects became Jupiter's outer irregular moons, small rocky or icy bodies that orbit Jupiter in highly elliptical paths far from the planet. However, Jupiter's four largest moons, the Galilean satellites, likely formed in a different way, through a process similar to planetary formation, but on a much smaller scale within Jupiter's own gravitational domain. During Jupiter's formation, the planet was surrounded by its own miniature version of a protoplanetary disk, sometimes called a circumplanetary disk. This disk consisted of material that Jupiter had captured, but that hadn't yet fallen into the planet itself. Within this disk, the same accretion processes that formed planets around the Sun created moons around Jupiter. The largest of these moons, Ganymede, actually grew larger than the planet Mercury, demonstrating the enormous amount of material available in Jupiter's region during the early solar system. The heat generated during Jupiter's formation came from several sources, including the gravitational energy released as material fell toward the planet's center, the kinetic energy of impacting objects, and the compression of gas as it accumulated around the growing planet. This heat was so intense that Jupiter's interior likely remained molten or in a plasma state for millions of years after its formation. Even today, Jupiter continues to radiate about 1.67 times more energy into space than it receives from the Sun, largely due to the ongoing slow contraction and cooling of the planet's interior. Earth's formation process, while occurring in the same general time frame, followed a very different path due to its location in the inner solar system. Without access to the abundant ice and gas that enabled Jupiter's rapid growth, Earth formed through the much slower process of rocky planetesimal accretion. The final stages of Earth's formation involved a series of massive impacts, including one collision so large that it likely created our moon by ejecting a significant amount of material into orbit around the early Earth. These violent impacts kept Earth's surface molten for hundreds of millions of years, creating conditions completely different from Jupiter's gas-dominated environment. The different formation environments also explain why Earth developed a layered internal structure, while Jupiter remains more homogeneous throughout its interior. Earth's high formation temperatures and the differentiation process caused by massive impacts led to the separation of heavy metals like iron and nickel, which sank to form Earth's core. while lighter rocky materials rose toward the surface. Jupiter's formation in a cold, gas-rich environment and its rapid accretion of lightweight gases created a more gradual transition from the solid core through liquid metallic hydrogen to gaseous hydrogen and helium in the outer layers. The formation story of both planets also reveals why they ended up with such different atmospheric compositions. Earth's atmosphere has been heavily modified over billions of years through volcanic outgassing, the loss of lighter elements to space, and the effects of life processes that have created our current oxygen-rich atmosphere. Jupiter's massive gravitational field, by contrast, has allowed it to retain essentially the same atmospheric composition it acquired during its formation, preserving a record of the original solar nebula's composition. The success of Jupiter's formation as a gas giant may have been influenced by its position in what astronomers call the habitable zone for gas giant formation. This zone, located beyond the snow line but not so far from the sun that temperatures become too cold for rapid accretion, provided the optimal conditions for building large planetary cores quickly enough to capture significant amounts of gas before the protoplanetary disk dispersed. Planets that attempted to form closer to the sun couldn't grow large enough fast enough, while those forming much farther away may have grown too slowly to capture gas effectively. Understanding the formation, stories of Earth and Jupiter provides crucial insights into why our solar system has the structure it does today, with small rocky planets close to the sun and large gas giants in the outer regions. This arrangement, once thought to be the natural result of planetary formation, is now known to be just one of many possible outcomes. The discovery of hot Jupiters, massive gas giant planets orbiting very close to their stars, and other unusual planetary system architectures around distant stars has shown that planetary formation can proceed in many different ways, depending on the specific conditions in each protoplanetary disk. The formation of Jupiter as such a massive planet has had lasting effects on the entire solar system that continue to this day. Jupiter's gravitational influence helped shape the asteroid belt, prevented the formation of a planet between Mars and Jupiter, and continues to protect the inner solar system from many potentially dangerous comets and asteroids. Without Jupiter's formation as a gas giant, Earth's own formation and evolution might have proceeded very differently, potentially creating conditions unsuitable for the development of complex life. In this way, the formation story of both planets is intimately connected, showing how the early history of our solar system created the conditions that ultimately made Earth a habitable world, while Jupiter became the massive guardian giant that continues to influence our cosmic neighborhood billions of years after its formation. As we near the end of our journey exploring Jupiter's incredible size compared to Earth, it's time to step back and truly absorb the mind-bending implications of what we've discovered. The numbers and comparisons we've explored so far tell an amazing story. But to really understand the scale we're dealing with, we need to examine Jupiter from perspectives that push the boundaries of human imagination. These scale perspectives will help you visualize just how dramatically different our universe would appear if Jupiter played a more prominent role in our daily experience, and they'll reveal cosmic relationships that demonstrate how size and distance work together to create the stable, life-supporting solar system we call home. Imagine for a moment that Jupiter suddenly appeared in our night sky at the same distance as our Moon, roughly 300 84,400 kilometers from Earth. The Moon currently appears about half a degree across in our sky, roughly the size of your thumbnail held at arm's length. Jupiter, with its diameter of 142,984 kilometers, compared to the Moon's 3,474 kilometers, would appear about 41 times larger across the sky. Instead of a small, bright disk that you can easily cover with your thumb, Jupiter would dominate the entire sky from horizon to horizon, appearing as an enormous sphere of swirling orange and brown clouds that would be visible even during daylight hours. The Great Red Spot alone would appear larger in our sky than the full moon currently does, creating a cosmic eye staring down at Earth with an intensity that would fundamentally change human culture and mythology. This massive Jupiter hanging in our sky would exhibit phases just like our moon does, but on a scale that would be absolutely breathtaking. During a new Jupiter phase, when the Sun would be behind Jupiter, from Earth's perspective, our planet would be plunged into an extended eclipse lasting for hours as Jupiter's massive bulk blocked out our primary source of light and heat. During a full Jupiter phase, the fully illuminated face of this giant planet would provide enough reflected sunlight to read by at night, turning nighttime into a kind of orange-tinted twilight that would make sleeping nearly impossible without thick curtains or blinds. The gravitational effects of having Jupiter so close to Earth would be catastrophic for our planet. Jupiter's powerful gravitational field would create tidal forces thousands of times stronger than those created by our moon. While the moon's gravity currently raises ocean tides by a few meters, Jupiter's proximity would create tidal forces strong enough to deform Earth's solid crust by hundreds of meters twice each day. These extreme tidal forces would generate so much friction within Earth's interior that our planet would become volcanically active beyond anything we can imagine, with constant earthquakes and massive volcanic eruptions reshaping the surface continuously. To put Jupiter's scale in a different perspective, consider what would happen if we could somehow shrink our entire solar system down so that Earth became the size of a marble, measuring about 1.3 centimeters in diameter. At this scale, Jupiter would be a sphere about 14.5 centimeters across, roughly the size of a large grapefruit or small basketball. The Sun would measure about 1.4 meters in diameter, roughly the height of a person, and would be located about 15 meters away from our marble-sized Earth. Jupiter would orbit this person-sized Sun at a distance of about 79 meters, nearly the length of a football field. Even at this dramatically reduced scale, the distances involved in our solar system are so vast that Jupiter would appear as just a distant ball across a football field from our marble Earth. Consider the perspective of someone living on Jupiter's moon Europa, one of the most fascinating worlds in our solar system. Europa orbits Jupiter at a distance of about 670,900 kilometers, roughly 1.75 times the distance between Earth and our moon. From Europa's surface, Jupiter would appear about 24 times larger in the sky than our moon appears from Earth. This massive planet would be a constant presence in Europa's sky, showing different faces as both Jupiter and Europa rotate, creating a complex dance of light and shadow across Europa's icy surface. The radiation from Jupiter's powerful magnetic field would create spectacular auroras in Europa's thin atmosphere, painting the sky with colors and patterns that would make Earth's northern lights seem pale by comparison. The concept of volume provides perhaps the most mind-bending perspective on Jupiter's scale. We've established that Jupiter's volume is about 1,321 times larger than Earth's volume. But let's explore what this really means in practical terms. If Jupiter were hollow and we wanted to fill it with Earth-sized spheres, we would need to somehow obtain 1,321 complete copies of our entire world. Each of these Earth copies would contain every mountain range, every ocean, every continent, every city, and every person who has ever lived. The Amazon rainforest would exist 1,321 times over. The Pacific Ocean would be replicated more than 1,000 times, and Mount Everest would have 1,321 identical counterparts scattered throughout Jupiter's interior. From the perspective of cosmic distance, Jupiter's influence extends far beyond its physical boundaries through its gravitational field. The Hill sphere, representing the region where Jupiter's gravity dominates over the Sun's gravitational influence, extends about 53 million kilometers from Jupiter's center. To put this in perspective, this gravitational sphere of influence has a diameter roughly one-third the distance between Earth and the Sun. Within this enormous region of space, Jupiter controls the motion of its 95 known moons and countless smaller objects, creating a gravitational empire that dwarfs the Earth-Moon system in both size and complexity. The timescales involved in Jupiter's rotation provide another fascinating perspective on its massive scale. Jupiter completes one full rotation in just 9 hours and 56 minutes, making it the fastest spinning planet in our solar system despite its enormous size. This means that a point on Jupiter's equator travels at about 45,300 kilometers per hour as the planet rotates. To put this speed in perspective, if you could somehow stand on Jupiter's equator, you would be moving fast enough to circle Earth's entire equator in just 53 minutes. This incredible rotational velocity, combined with Jupiter's massive size, creates centrifugal forces strong enough to noticeably flatten the planet, making Jupiter's equatorial diameter about 9,275 kilometers larger than its polar diameter. Consider the perspective of atmospheric scale when comparing Earth's thin atmospheric envelope to Jupiter's massive gaseous bulk. Earth's atmosphere has a mass of about 5.15 trillion kilograms, which sounds enormous, but represents only about 0.000086% of Earth's total mass. Jupiter's atmosphere, by contrast, makes up the vast majority of the planet's total mass, with no clear boundary between atmosphere and interior. If we could somehow extract all of Jupiter's atmospheric gases and compress them to Earth's atmospheric density, this material would form a gaseous envelope extending millions of kilometers into space, completely engulfing not just Earth, but potentially the entire orbit of our moon. The energy scales involved in Jupiter's internal processes provide yet another mind-bending perspective. Jupiter radiates about 1.67 times more energy into space than it receives from the Sun, generating this excess heat through the slow gravitational compression of its massive bulk. The total energy output from Jupiter's interior equals about 335 trillion watts, roughly 75,000 times more energy than all of human civilization currently produces. This internal heat source means that Jupiter would continue to glow dimly in infrared light, even if the Sun suddenly disappeared, making it a miniature star that never quite achieved the mass necessary to ignite nuclear fusion. From the perspective of magnetic field strength, Jupiter's magnetosphere creates a region of electromagnetic influence that extends far beyond the planet's physical boundaries. Jupiter's magnetic field is about 20,000 times stronger than Earth's magnetic field, creating a magnetosphere so large that it extends well beyond the orbits of Jupiter's four largest moons. If we could somehow see magnetic field lines with our eyes, Jupiter would appear surrounded by an enormous bubble of twisted, complex magnetic field structures extending millions of kilometers in all directions, with Jupiter itself appearing as just a small sphere at the center of this vast electromagnetic domain. The perspective of surface area provides another way to comprehend Jupiter's incredible scale. Jupiter's surface area, measured at the level of its visible cloud tops, covers approximately 61.42 billion square kilometers compared to Earth's surface area of 510 million square kilometers. This means that Jupiter has about 120 times more surface area than Earth. To visualize this difference, imagine being able to unwrap Jupiter's surface like peeling an enormous orange and laying it flat. The resulting surface would be large enough to contain 120 complete copies of Earth's entire surface, including all continents, oceans, deserts, forests, cities, and everything else that covers our planet. The weather systems on Jupiter operate on scales that dwarf anything we experience on Earth, providing perspective on how size affects atmospheric dynamics. The Great Red Spot, Jupiter's most famous atmospheric feature, is a storm system that measures about 16,350 kilometers across, larger than Earth's entire diameter. This storm has been raging continuously for at least 400 years, possibly much longer, powered by heat from Jupiter's interior and the complex interactions between different atmospheric layers. Wind speeds within this storm reach up to 432 kilometers per hour, fast enough to circle Earth's equator in less than 3 days. The energy contained within this single storm system exceeds the total energy of all hurricanes, tornadoes, and other severe weather events on Earth combined over many years. From the perspective of gravitational binding energy, Jupiter's massive gravitational field holds its enormous bulk together with forces that dwarf anything we experience on Earth. The gravitational binding energy of Jupiter, representing the total energy that would be required to completely disassemble the planet and disperse all its material to infinity, equals approximately 2 times 10 to the 36th power joules. This number is so large that it defies easy comparison, but it represents roughly the total energy output of our Sun over a period of about 60,000 years. This enormous binding energy explains why Jupiter has maintained its structure and composition essentially unchanged for billions of years, despite the various forces acting upon it. The perspective of orbital mechanics reveals how Jupiter's massive size translates into gravitational influence throughout the solar system. Jupiter's gravity affects the orbits of asteroids, creating gaps in the asteroid belt called Kirkwood gaps, where objects cannot maintain stable orbits due to gravitational resonances. Jupiter also captures comets that venture too close, either destroying them through tidal forces or deflecting them into new orbits. Some estimates suggest that Jupiter has prevented thousands of potentially dangerous comets and asteroids from entering the inner solar system over the past billion years, acting as a gravitational shield that has helped protect Earth from catastrophic impacts. As we contemplate these mind-bending scale perspectives, we begin to understand that Jupiter represents more than just a large planet in our solar system. It's a world so massive and influential that it fundamentally shapes the structure and behavior of our entire cosmic neighborhood. Every one of these perspectives reveals new aspects of Jupiter's incredible scale, from the visual impact it would have if placed closer to Earth, to the vast regions of space it influences through gravity and magnetism, to the enormous energies involved in maintaining its structure and driving its atmospheric dynamics. These perspectives help us appreciate not just how big Jupiter is, but how this size translates into cosmic power and influence that has shaped the formation and evolution of our solar system for billions of years, creating the stable, protected environment that has allowed life to flourish on our small, rocky world. Now that we've explored Jupiter's incredible size compared to Earth from every possible angle, it's time to zoom out even further and place both of these worlds in the vast context of our universe. While Jupiter may seem like an absolute giant when compared to Earth, and while it dominates our solar system with its massive presence, the cosmic perspective reveals that both Earth and Jupiter are actually tiny specks in an incomprehensibly vast universe filled with objects that make even Jupiter look small. This cosmic context doesn't diminish the wonder of Jupiter's scale compared to Earth, but rather places both worlds in the grand hierarchy of cosmic objects that stretches from the smallest particles to the largest structures in the observable universe. Let's begin our cosmic journey by comparing Jupiter to our Sun, the star that provides energy for our entire solar system and serves as the gravitational anchor that keeps all the planets in their orbits. The Sun contains about 99.86% of all the mass in our solar system, which means that Jupiter, despite its dominance among the planets, represents only a tiny fraction of our solar system's total mass. The Sun's diameter measures approximately 1.39 million kilometers, making it about 9.7 times wider than Jupiter and about 109 times wider than Earth. When we consider volume, the Sun could contain about 1,300 Jupiter-sized spheres, or roughly 1.3 million Earth-sized spheres, demonstrating that even our massive gas giant is utterly dwarfed by our relatively ordinary star. The mass comparison between Jupiter and the Sun reveals the true scale of stellar objects. The Sun contains about 1,048 times more mass than Jupiter, which means you would need more than 1,000 Jupiter-sized planets to equal the mass of our single star. If we wanted to balance the Sun on a cosmic scale using Earth's, we would need approximately 333,000 Earth-sized planets on the other side. This comparison helps us understand why the Sun's gravity dominates our solar system so completely, keeping planets in stable orbits across billions of kilometers of space and maintaining the delicate balance that has allowed our solar system to remain stable for billions of years. Yet even our Sun, massive as it is compared to the planets, is just an ordinary middle-aged star among the hundreds of billions of stars that make up our Milky Way galaxy. Many stars are much larger than our Sun, with some red supergiant stars measuring hundreds of times the Sun's diameter. If we placed one of these supergiant stars, such as Betelgeuse or Antares, at the center of our solar system, its surface would extend beyond the orbit of Mars, completely engulfing Mercury, Venus, Earth, and possibly Mars as well. Jupiter would orbit within the outer atmosphere of such a star, giving us perspective on just how large some cosmic objects can become. The discovery of exoplanets, planets orbiting other stars, has provided fascinating insights into how Jupiter compares to planets throughout our galaxy. Astronomers have discovered thousands of exoplanets since the 1990s, and many of these are gas giants similar to Jupiter, but with a wide range of sizes and masses. Some exoplanets, called superjupiters, contain several times more mass than our Jupiter, while others are smaller gas giants that fall between Jupiter and Neptune in size. The most massive planets discovered so far contain up to 13 times Jupiter's mass, approaching the boundary where they would become brown dwarf stars rather than planets. Hot Jupiters represent one of the most surprising types of exoplanets discovered, challenging our understanding of planetary formation and migration. These are Jupiter-sized or larger planets that orbit extremely close to their parent stars, completing full orbits in just a few days rather than the 12 years it takes Jupiter to orbit our Sun. The temperatures on these hot Jupiters can exceed 2,000 degrees Celsius, hot enough to melt metals and create exotic atmospheric conditions, unlike anything in our solar system. The discovery of these hot Jupiters has shown that planetary systems can have architectures completely different from our own, where massive gas giants migrate inward from their formation locations to orbit close to their stars. The concept of brown dwarf stars provides another interesting point of comparison for understanding Jupiter's place in the cosmic hierarchy. Brown dwarfs are objects that are more massive than planets, but not massive enough to sustain nuclear fusion like true stars. They typically contain between 13 and 80 times Jupiter's mass, representing a class of objects that bridges the gap between planets and stars. Some brown dwarfs are cool enough to have atmospheres with temperatures similar to Jupiter's, yet they generate their own heat through gravitational compression, rather than relying on energy from a nearby star. When we consider the largest possible planets, we encounter theoretical limits imposed by the physics of matter and gravity. As planets become more massive, their increased gravitational fields compress their material to higher densities, which can actually cause them to become smaller rather than larger. The largest possible rocky planets might be only about twice Earth's radius, while the largest possible gas giants might be only slightly larger than Jupiter, despite containing much more mass. This means that Jupiter is actually close to the maximum size that a gas giant planet can achieve, making it a near-perfect example of this type of world. The age of Jupiter compared to the age of the universe provides another aspect of cosmic context. Jupiter formed about 4.6 billion years ago, relatively early in the history of our solar system. The universe itself is approximately 13.8 billion years old, which means Jupiter has existed for about one-third of cosmic history. During the billions of years since Jupiter's formation, it has maintained a remarkably stable structure and orbit, demonstrating the long-term stability that massive gas giants can achieve. This stability has been crucial for maintaining the orbital stability of the inner planets, including Earth, over geological timescales. The role of Jupiter-like planets in other solar systems has become an important area of astronomical research. Computer simulations suggest that the presence of a massive gas giant in the outer regions of a planetary system can help maintain the orbital stability of smaller, rocky planets in the inner regions. This protective effect occurs because the massive planet's gravity prevents smaller objects from developing highly elliptical orbits that might destabilize the interplanetary system. The search for Earth-like exoplanets often focuses on systems that contain Jupiter-like planets in similar orbital positions, as these systems may be more likely to harbor stable, habitable worlds. Galaxy scale perspectives reveal how tiny both Earth and Jupiter are, compared to the vast structures that organize matter on cosmic scales. Our Milky Way galaxy contains an estimated 100 to 400 billion stars, most of which likely have planetary systems of their own. If even a small percentage of these stars have Jupiter-like planets, there could be billions of gas giants similar to our Jupiter scattered throughout our galaxy alone. The observable universe contains an estimated 100 billion galaxies, suggesting that Jupiter-like planets may be among the most common types of worlds in the cosmos. The formation of heavy elements necessary for planet formation provides crucial cosmic context for understanding how worlds like Earth and Jupiter came to exist. The hydrogen and helium that make up most of Jupiter's mass were created during the Big Bang, making Jupiter partly composed of some of the oldest matter in the universe. However, the heavier elements that make up Jupiter's core and all of Earth's mass were forged inside earlier generations of massive stars and distributed throughout space when these stars exploded as supernovas. This means that both Earth and Jupiter are made from recycled stellar material, connecting our solar system to cosmic processes that occurred billions of years before our sun was born. The concept of habitable zones around stars provides another important aspect of cosmic context. Earth orbits within our sun's habitable zone, the region where liquid water can exist on a planet's surface. Jupiter orbits far outside this zone, where temperatures are too cold for liquid water to exist without internal heat sources. However, some of Jupiter's moons, particularly Europa and Enceladus, may harbor subsurface oceans heated by tidal forces from their parent planet's gravity. This suggests that gas giants like Jupiter might actually help create habitable environments for life, even when the planets themselves orbit outside their star's traditional habitable zone. The search for life in the universe often focuses on Earth-like planets in habitable zones, but the study of Jupiter and its moons has expanded our understanding of where life might exist. The discovery of complex organic molecules in the atmospheres of gas giants and the possibility of life in the subsurface oceans of their moons suggests that Jupiter-like systems might actually be more common locations for life than Earth-like planets. This possibility has profound implications for our understanding of how common life might be throughout the universe. Dark matter and dark energy, which together make up about 95% of the universe, provide the ultimate cosmic context for understanding ordinary matter like that which makes up Earth and Jupiter. All the stars, planets, galaxies, and other visible objects in the universe represent only about 5% of the total mass and energy content of the cosmos. This means that both Earth and Jupiter, despite their local importance to us, are made from a tiny fraction of the types of matter and energy that actually dominate the universe. The gravitational effects of dark matter helped shape the large-scale structure of the universe and influence the formation of galaxies like our Milky Way, indirectly affecting the conditions that allowed our solar system to form. The ultimate fate of Jupiter provides a sobering cosmic perspective on the temporary nature of planetary systems. In about 5 billion years, our sun will begin to run out of nuclear fuel and start expanding into a red giant star. During this phase, the sun's outer layers may extend beyond Earth's orbit, completely engulfing the inner planets. Jupiter, located farther from the sun, will likely survive this red giant phase but will experience dramatic changes as increased solar radiation heats its atmosphere and potentially strips away some of its outer layers. Eventually, the Sun will shed its outer layers and become a white dwarf star, leaving Jupiter and the other outer planets orbiting a much fainter, slowly cooling stellar remnant. As we contemplate Jupiter's place in this vast cosmic context, we gain a profound appreciation for both the scale of our gas giant neighbor and the incredible diversity of worlds that exist throughout the universe. Jupiter may be tiny compared to stars and negligible compared to galaxies, but it represents a perfect example of one of the most common types of worlds in the cosmos. The same physical processes that created Jupiter's massive size and gravitational dominance are likely creating similar worlds around countless other stars throughout our galaxy and beyond. This cosmic perspective doesn't diminish the wonder of Jupiter's incredible scale compared to Earth, but rather enhances it by showing us how both worlds fit into the grand cosmic story of matter, energy, and gravity working together to create the rich diversity of objects we observe throughout the universe. From the smallest particles to the largest galactic structures, from the Big Bang to the far future of our solar system, both Earth and Jupiter play their parts in an ongoing cosmic drama that has been unfolding for nearly 14 billion years and will continue for trillions of years to come. If you've enjoyed this incredible journey through the mind-bending scale differences between Earth and Jupiter, and if these cosmic perspectives have expanded your understanding of our place in the universe, please show your support by hitting that like button and subscribing to the Lazy Cosmos. Your engagement helps us continue exploring the most fascinating aspects of space and science, bringing you more amazing discoveries about the incredible universe we all call home. Don't forget to ring that notification bell so you never miss our latest adventures into the cosmic unknown, and let us know in the comments which aspect of Jupiter's massive scale surprised you the most.